If everybody could take a seat, we're about to get started. So welcome to Geo-Risk 2023. We are very pleased to be hosting this event in the capital of the United States of America. And I want to tell you a little bit about this land. We acknowledge that the land comprising present-day Arlington County is the ancestral home and hunting ground of the Dogue and Toxinot, Pamunkey, and Piscataway people, many within the Algonquin language group, and some within the Powhatan Paramount chiefdom. My name is Bob Gilbert. I'm the immediate past president of the Geo-Institute of the American Society of Civil Engineers, also headquartered here in Washington, D.C. The GI is an international organization with over 12,000 members. Our mission is to advance the geo profession and enhance the value of geoprofessionals. And this specialty conference is a great example of us taking a step in the right direction in achieving that mission. This is our first specialty conference since the pandemic to be held without postponement and entirely in person, and we very much look forward to what the next 3 days will bring. Thank you. I'm going to turn it over to Limin Zhang, one of the co-chairs of this conference.
Good morning, everybody. My name is Limin Zhang from Hong Kong University of Science and Technology. I'm past chair of Risk Assessment and Management Committee of Geo-Institute. It's my great honor to welcome you. And if you need any help during the conference, please feel free to contact us. Thank you.
All right, good morning, everybody. My name is Shadi Najjar, and I am the co-chair of Geo-Risk 2023 also. It gives me great pleasure to welcome you all to the third version of Geo-Risk. Before we kick off the exceptional technical program that we have, I want to thank everybody who contributed to making Geo-Risk 2023 a reality. This includes the conference co-chairs, the conference technical committee, and the full organizing committee, which you can see on the screen. So I would like to send them special thanks, and I would like to add the special thanks to the GI members, the GI leadership, and the GI staff for their tremendous support in the organization. So please join me in thanking them all for the commitment and for their time. So without further ado, I would like to call Professor KK Poon to the stage to introduce our Suzanne Lacasse Lecturer. KK, the floor is yours.
Great. All right, thank you. Thanks, Shadi. Good morning, everybody. My name is KK. I'm from the Singapore Technical University of Design. Very happy to be here, and I would like to thank Bob, Limin, and Shadi for giving me the honor to introduce the Suzanne Lacasse Lecture. If you don't mind, I'm making this presentation in part on behalf of Professor Michael Hicks, who is the chair of TC 304. The Suzanne Lacasse Lecture is one of the several prestigious honors lecture hosted under ISSMGE. Just a few words. I'm sure everybody recognizes Dr. Suzanne Lacasse. This honor lecture was established in 2015, and it's actually in honor of the fact that she brought the impact of risk assessment to practice. That is something that's highly recognizable. I do not think that I need to introduce her further. She has delivered both the Rankine lecture and also the Terzaghi lecture. This lecture has been ongoing. This lecture would be number 7 this morning. I just found out while I was preparing the slides last night that I'm actually very surprised that somehow you guys have managed to assemble every Suzanne Lacasse Lecturer in Geo-Risk 2023. I'm not sure how you do it, but it's quite amazing. We should take a picture together later. So you get to talk to everybody. For a conference that's about risk and uncertainty, we're actually not very uncertain. I have the great privilege here this morning to introduce Professor Jianye Ching. I'm sure many of you would know him. Professor Ching completed his PhD in 2002. That's in UC Berkeley. Ever since then, he has actually been serving as in his role in National Taiwan University as a professor. He's most actually well known for his work. You could see risk and reliability in spatial variability, a topic that you'll be discussing this morning, as well as data analytics and machine learning that I'll be sharing this afternoon. He's a very close collaborator of mine. Some of you may not know, actually, besides his exceptional breakthrough work in geotechnical engineering, he's actually very well known in the structural reliability community at large. That's not something that he will be sharing. One of the topics that I would like to mention is big data, and Prof. Chin, one of his most classical paper, I just show one. This is in 2014, where he assembled one of the largest soil property database, which I think is still the largest as of today. And maybe just to get us started on the right footing, I need to show him some interesting photo. This was me and Professor Chin many years ago, National Taiwan University. If you have never been there, you should take a look. It's a very beautiful university. And the only reason I'm there is not to talk about risk or reliability. The reason I'm there is that the food in Taipei is really good. So I would stop here, and I'll invite Professor Chin to deliver his lecture. Thank you so much.
Thank you, KK. Well, that photo was more than 15 years ago, 12 years ago. So the topic I want to share today is about one of the my research main direction, spatial variability from point process, spatial average to mobilized value. This topic is quite fundamental. I will probably spend most of the time in point process. If I have sufficient time, I will talk about more about mobilized value. And how do we do that? Oh, okay. First, thank all the co-chairs for allowing me to deliver this lectures in this conference. Also want to thank Suzanne and also all the TC304 members for electing me as the lecturers. My collaborators for this line of research include Professor KK Fung and Professor Ikumasa Yoshida, and also Professor Marcos Uzili in Italy, and also my graduate students. Geotechnical spatial variability, today I will focusing on point process. For point process, I mean, this is the spatial variation of some soil property about the depths. At a certain depth, the property is uncertain. So if we focus on the entire profile, we call this entire profile as the point process. For spatial average, I mean, if we are not just interested in the profile, but we're interested in the spatial average of the some values, so property values over some intervals. That's what I mean by a spatial average. In the end, mobilized value is kind of the properties that is mobilized in the end in terms of limit state of concern. It is like the property that a geotechnical system actually fills. So let me start from point process and the spatial average. I actually will spend most of the time in point process. This is probably the most fundamental and most important topic. And this is probably this figure we have seen a lot. This is from Foom and Kauhaui. And usually we say property point process can be decomposed into trend and the spatial variability. By trend, I mean there seems to be a linearly increasing trend for this particular example. And spatial variability is the difference between the actual soil property and the trend. The spatial variability part, usually we model it as a zero mean stationary random field. And there are two basic parameters for this model. The first is the standard deviation. The second is called the scale of fluctuation, delta. This measures the distance between within which the soil property shows strong correlation. How about spatial average? Why spatial average is important? Here I quote two statements, two well-known statements. One is from Professor Van Mark in his classical paper in 1977. He says that the exact probability density shape of point process may be even less important. What is often needed is the probability density function of some spatially average soil properties. Say, for instance, if we're talking about a pile, a friction pile, the shaft resistance governs the performance of the pile. The shaft resistance is the result of a spatial average along the shaft. So the performance of the pile is more related to the spatial average rather than some point value. Also, Eurocode 7 has some similar statement. It says that the volume of the soil involved in a limit state in the ground is much larger than the volume of a test sample. Therefore, the test results have to be averaged over the volume of soil involved in the limit state considered. So spatial average seems to be important. And one important conclusion that Professor Van Mark got is that the consequence of spatial average is that the mean value of the spatial average, it doesn't change. It remains the same as a point process. What is changed is called the variance reduction. The variance of the spatial average value is less than the variance of the point value. That's the main conclusion that Professor Van Mark pointed out. And this variance reduction is called variance reduction function. And he further finds that this is the variance reduction function. He further finds that this variance reduction function, it is insensitive to the choice of the autocorrelation function. For those of you who know autocorrelation function, it is the function that describes how the autocorrelation decays with the distance, but between two spatial points. There are some well-known autocorrelation function model, such as single exponential model or square exponential model. And it turns out that it doesn't matter which model you take. You take a square exponential model, which is this form, single exponential model, which is that form. The variance reduction function, it seems quite insensitive to the type of the autocorrelation function. So one possible conclusion is that the spatial average, the effect of spatial average, it seems to be insensitive to the autocorrelation function type. So main takeaway is that spatial average is more relevant than point process. Second, spatial average is governed by variance reduction function, which in turn governed by the scope of fluctuation. And finally, autocorrelation function type has limited effect on variance reduction function. But is that true that the autocorrelation function type, it really has a very small effect on the performance of a geotechnical structure? That's the question I want to ask for the next few PPTs. Professor Venmark says that spatial average, the type of autocorrelation function seems to have limited effect on the spatial average. But it is the spatial average over a prescribed region. Okay. Now the key question is that true that autocorrelation function also has a limited effect on the performance of a geotechnical structure? To address this question, we consider the Whittle-Mayterm autocorrelation model. This model is more complicated than the traditional autocorrelation model, such as single exponential or square exponential. There's one more parameter here. It is called the new parameter. This parameter controls the smoothness of the random field. To show you the effect of the smoothness, this is the random field sample when the smoothness parameter equals to 0.5, which is the same as the single exponential model. This is the random field sample when the smoothness equals to infinity, which is the same as the square exponential model. So it seems that different types of autocorrelation function has different smoothness. Is that true that different smoothness has no effect on the performance of the no effect on the performance of a geotechnical structure? Yeah, we test that. Okay. Here we first consider a friction pile as our geotechnical structure. Friction pile is its performance is controlled by the spatial average over a prescribed domain, which is the shaft area. Indeed, for this situation, Professor Venmark's conclusion is exactly quite right. Because you see this horizontal axis is the smoothness. As you can see, the failure probability of this frictional pile is nearly constant with respect to the change of smoothness. That means smoothness seems to have no effect on the performance of this friction pile. But this is because the friction pile its performance is totally governed by the spatial average over a prescribed domain. Okay. If we change the example to an infinite slope, consider an infinite slope. Suppose the variation of soil property, it varies in the direction that is perpendicular to the slope surface. Okay? And suppose, consider two situations. Suppose the variation, the autocorrelation model is single exponential. So you get this very non-smooth variation of soil strength over this, the perpendicular direction. The other example is, it is square exponential model, which produce very smooth variation. Suppose those two scenarios have exactly the same scale of fluctuation and also standard deviation. Which scenario do you guess will be more dangerous? The answer is single exponential. This one is more dangerous because this one gives you very many local small-scale local oscillation. And that kind of small-scale local oscillation give you more possibility to create local weak thing. And that local weak thing will produce many local weak region so that the infinite slope may fail more probably, more likely to happen. So this is a more dangerous situation. And actually, you can see the failure probability of this infinite slope. It is quite large when the smoothness parameter is small compared when it is large. So smoothness indeed has some effect on the performance of this slope. So there seems to be some contradiction here, but I can tell you there is no contradiction. I mean, the finding here does not contradict to what Professor Van Mark said. Professor Van Mark said that the type of autocorrelation function has limited effect to the spatial average over a prescribed domain. Over a prescribed domain. However, this infinite slope problem, its performance is not governed by spatial average over a prescribed domain. Actually, the location of the failure surface, it is emerging. It is random. Let me show you another example. Sorry about this. Two soil column, subjected to compressive loading. The first soil column, the two-dimensional random field of shear strength is generated by single exponential model, so you see all the local roughness. The second is generated by the square exponential model. You see all the smooth variation. And those two random fields, they have exactly the same scale of fluctuation and the standard deviation. Which one do you guess is more dangerous? The second one, the smooth one. The smooth one. That's what we discover. When the smoothness is higher, then you get higher probability of failure. This shows that the effect of smoothness, there is some effect of smoothness on the performance of soil, of geotechnical structure. And the effect is quite unpredictable. For some situation, smooth process is good, but for the other, smooth process is not good. It is not good. So key takeaway is that it is indeed correct that autocorrelation function type has not much effect on spatial average over a prescribed domain. But it may not be true that the type of autocorrelation function or smoothness has no effect on the performance of a geotechnical structure. Because the performance of some geotechnical structure, they are not just about spatial average over a prescribed domain. Yeah, so smoothness may be an important parameter. So now, how do can we identify smoothness using, say, a CPT data? We all know that we can identify scale of fluctuation using CPT data, but can we also identify smoothness? The answer is depends. There are two basic requirements. The first is that you need to have a non-traditional autocorrelation model such as Whittle matrix model. You need to have a model with a smoothness parameter in it. Second, you cannot use method of moments. You probably need to use something like a maximum likelihood. For method of moments, I mean, this is a very common way of determining scale fluctuation. You plot your empirical autocorrelation function data, and then you fit your autocorrelation function model. That method is not able to identify smoothness because the different the autocorrelation model with different smoothness, the main difference is that whether the autocorrelation function is differentiable or not at the origin, at that point. At that point. Method of moments is sensitive to the total area, but it is insensitive to what is the tangent slope at that point. So we probably need, you use maximum likelihood, you can identify both scale of fluctuation and the smoothness. And this is one case study that we tried. Here we actually use maximum likelihood for this Hollywood site. In this site, there are 25 CPTs, vertical CPTs. For each CPT, we identify its scale of fluctuation and the smoothness using maximum likelihood. And this is what we get. Horizontal axis is smoothness. Vertical axis is scale of fluctuation. The identified scale of fluctuation is quite consistent to the range that the original author got. But we also be able to get the smoothness. And recently, we investigate, we compile this global CPT database. This database contains more than 1,000 soundings from 59 sites worldwide. And we extract more than 300 detrended homogeneous soil elements. And we analyze the detrended QT data using the maximum likelihood to see what is the scale of fluctuation and the smoothness. And this is the result we got. There are hundreds of CPTs here. Horizontal axis is smoothness. This is vertical scale fluctuation. We found that the identified smoothness, it is actually quite narrow. Nu is, for most of the cases, nu is just between 0.1 to 2. 0.1 to 2. And also, vertical scale fluctuation, vertical scale fluctuation is also quite narrow. It's mostly is greater than 0.1 meter and less than 1 meter. Oh. And this result is quite interesting. Smoothness is mostly between 0.1 to 2.5. It means that the square exponential model is not a realistic model for the spatial variability. Square exponential model is quite commonly used for many people, but my suggestion is that if your purpose is to model the spatial variability part, square exponential model is not a realistic model. Single exponential model is, and second order Markov model is also realistic, but square exponential model is not realistic. That's for the vertical scale fluctuation and for the vertical smoothness. The main difficulty for the identification lies in how do we identify horizontal scale fluctuation and the horizontal smoothness. It is difficult because most of the CPT are done in the vertical direction. People don't do horizontal CPTs. So you don't have CPT data with closely spacing horizontally data. That makes the horizontal identification difficult. But luckily, we have this very interesting case study by Mark Jaksa in his PhD thesis. There are more than 200 CPT in a site. In particular, very closely spacing, there are 51 CPT with 0.5 meter spacing. Okay, so we analyze this data set. This is a visualization of the data set. This is the horizontal coordinate. That is the depth. This is the QT value. As you can see, the data seems to be quite spatial variable, even in the horizontal direction. And for this, this is the not surprising that vertical scale fluctuation and smoothness is quite identifiable. But for the vertical scale fluctuation, for the horizontal scale fluctuation and the horizontal smoothness, it is not identifiable. The red dots here means here we are doing Bayesian analysis. So the yellow dots shows the posterior samples for the horizontal scale fluctuation and the horizontal smoothness. You see, even for this very closely spacing CPT data, horizontal parameters are not really identifiable. We can only identify the upper bound for the horizontal scale fluctuation. We only know that horizontal scale fluctuation is less than 0.4. Less than 0.4. Well, for the people here, you know about the horizontal scale fluctuation divided by the vertical scale fluctuation ratio. That ratio, usually we thought that ratio is about 10 or 20 or even 100. But I can tell you for this particular site, no, that ratio is actually less than 1. How come we know that it is less than 1? For this particular site, Professor Mark Jaksa, they actually did a horizontal CPT. One horizontal CPT. That's the only horizontal CPT we can find in the literature. They did it. at the same site. And we also analyze that horizontal CBT. That's its horizontal scale fluctuation and the smoothness. The horizontal smoothness is very similar to the vertical smoothness. But horizontal scale fluctuation is actually less than the vertical scale fluctuation. You may think this is a rare case, but I can show you later that this may not be a rare case. This may not be a rare case. Okay, this is another example recently done by Dr. Dept on a dike in the Netherlands. They also have this densely spacing data along the dike direction, and this is the data. For this particular site, fortunately, the horizontal scale fluctuation is identifiable. And the resulting horizontal scale fluctuation is still less than 1 meter. So horizontal scale fluctuation, I mean, including myself, previously before we did this analysis, we always thought that horizontal scale fluctuation is large. It may be 10 meter or 20 meter or even 100 meter. But real case history shows that it may not be the case. It may not be the case. Okay, those are the two examples. We actually analyzed, recently we analyzed 28 examples with multiple CPTs to try to identify horizontal parameters. And this is the result we got. This is the result we got. Okay. This is the number of soundings. You see, for most of the sites, we have more than 10 soundings. And again, we detrend first before we do the analysis. And this shows the minimum and the maximum horizontal distance between between all the soundings. This shows the identified vertical scale fluctuation and the smoothness for those case histories. Well, the result you see here is consistent to what we have mentioned to you here. You see the identified vertical smoothness, it ranges in a narrow range. Vertical scale fluctuation, it is also narrow. However, for all the cases, for most of the cases, we are only able to identify the upper bound of the horizontal scale fluctuation. The only 3 cases we successfully identified the horizontal scale fluctuation is, one case is this one. This is a church, Christchurch site. The identified horizontal scale fluctuation is 2 meter, quite small. And this one is the dike site that I mentioned to you. 0.9 meter is also quite small. This one is Mark Jaksar's case. Horizontal scale fluctuation, by the way, this one is identified using the single horizontal CPT. It's very small, very small. Okay, if you look at the identified upper bounds, the horizontal scale fluctuation, it seems to be not very large, although many of us thought they are large. Okay. Okay, key takeaway. Vertical scale fluctuation and smoothness are identifiable, usually, and they are within a narrow range. In contrast, horizontal parameters are hard to identify using vertical CPTs. Finally, horizontal scale fluctuation might not be much larger than vertical scale fluctuation as what we thought they are. Okay, now let me continue to talk about point process. A point process is an important topic. We mentioned that point process is usually assumed to be composed of the trend and the spatial variability part. We have finished the spatial variability part. How about the trend part? As I mentioned, the common model is that soil property is composed of the trend plus the spatial variability. Yeah, traditionally, the trend part is modeled by a deterministic polynomial, such as first order or second order polynomial, and the detrended data is modeled by random field. Professor Fenton, actually, he mentioned that the trend must be viewed with considerable caution. What he said that, what he meant is that if you do a CPT at this site and you fit a trend, the same trend, you probably cannot use the same trend for another site, even a nearby site. You probably cannot do that because at a nearby site, maybe the vertical trend changes. But I can tell you this statement is, of course, correct. But if we take a look at Professor Mark Jaxa's data at this site, you see from here to here, it is only like 20 meters away. You see, within this 20-meter horizontal distance, if you look at the vertical trend, it changes within this very short distance. So even when you get a trend at this CPT, the same trend may not be applicable to another CPT that is maybe 5 meters away. Okay. So trend is a difficult topic that we must consider it carefully. And in 2017, KK and myself, we proposed the idea that maybe we should also consider trend function as a uncertain function. Okay. And then we take some time on this modeling problem for an uncertain trend. And recently, my close friend, Professor Yoshida, he took another view for the trend that we think it is really interesting. He said that maybe we should also model the trend as a zero mean stationary Gaussian random field. So our total soil property is composed of trend and the spatial variability. Previously, we only considered spatial variability part as a random field. The trend part is considered as a polynomial. But because a trend is also might be also quite uncertain, how about we just consider both parts to be random field? Okay. But one important constraint is that the trend part is a smooth random field, which means that we use the square exponential model to model the trend part. The smoothness is infinity. the spatial variability part can be rough. And this model is quite interesting. This model actually is similar to the superimposed scale fluctuations discussed by Professor Van Mark paper. Professor Van Mark, he stated this, maybe his observation. He said that maybe the actual spatial variable data, it has more than one scale fluctuation. Maybe there are two scale fluctuations. Okay, let me skip all the calculation detail. Let's consider that this superimposed scale fluctuation model that is really interesting. So this example is the Mark-Jaksas data. This is the Mark-Jaksas data. And we try to model the trend using two ways. One way is the superimposed model. We call it a Gaussian process trend model. So this is Gaussian process trend. Another example is the traditional polynomial model. We used this this second-order polynomial to model the trend. This picture shows you the two possible trends for these two data to this data set. As you can see, this GPR trend model, it is able to follow the data trend quite well, better than the polynomial trend model. And this is the result we get using the GPR trend model. This is the vertical scale fluctuation and the vertical smoothness. Horizontal scale fluctuation, horizontal smoothness. This is a parameter identified using the polynomial trend model. This is the vertical parameter. This is the horizontal parameters. This result seems to be similar to that result, except that the identified vertical scale fluctuation for that model is a little bit higher than that. This is probably because this trend model is not as good as that model. So some of the trend data, they leak to the spatial variability part. And that leak part has larger scale of fluctuation. So you get a larger scale fluctuation here. This result is new. This result is the second. This is the identified horizontal and the vertical scale fluctuation for the trend part. That part is the superimposed scale fluctuation that Professor Van Mark is talking about. This is the scale fluctuation for the trend. Okay. And only GPR model has that result. Polynomial model don't have that result. Okay. One more. Okay. For the same site, we do this Li1 CPT out analysis. This result is quite interesting. We take one CPT out from the training data, and then we train the model that we have, and then we do a conditional random field simulation for that CPT that we took out. Okay, we call this Li1 out CPT validation. And this is the conditional random field simulation result for the GPR model. This is the CPT that we took out. You see the conditional random field. The dot line is the 95% confidence interval for the conditional random field, and the red line, solid line, is the median. The conditional random field follow the actual data quite well. However, if you adopt the polynomial trend, this is the result you get. It doesn't follow well. And more interestingly, let's consider this another CPT at x equals to 40. That CPT is in the training data, so this validation is not a real validation. All the conditional random field pass through that CPT. However, if you simulate your conditional random field 1 centimeter away from that CPT, you see, for this polynomial trend model, you get a fairly wide 95% confidence interval. You start to get uncertainty. Even if you move 1 centimeter away from the sounding data that is actually in the training data set. But for the GPR model, if you model the trend better, it seems okay. The 95% confidence interval, it only increased a little bit. So that shows the, okay, this is the final slide I want to show you. For the GPR trend model, we can identify two scale of fluctuation. One is for the trend, the other is for the spatial variability part. For the spatial variability part, we already seen it. For the vertical one, it varies within a narrow range. For the horizontal one, the scale fluctuation is small. It's also small. But if you look at the identified scale fluctuation for the trend part, this is the identified scale fluctuation for the trend. This is for the vertical direction. This is for the horizontal direction. Okay, quite interesting. I think it seems to me that for the spatial variability part, maybe the vertical parameter and the horizontal parameter, they are not so different. However, for the trend part, the horizontal trend scale fluctuation, it seems to be much larger than the vertical scale fluctuation of the trend. So in the past, we usually think that horizontal scale fluctuation is large and vertical scale fluctuation is small. That may be because the vertical scale fluctuation we get is from that part. However, the horizontal scale fluctuation we get, it may be from the trend part. It may be from the trend part. Very few people have seen the horizontal scale fluctuation for the spatial variability part. So my hypothesis is this. Maybe for the spatial variability part, vertical autocorrelation parameter may not be very different from the horizontal ones. But for the trend part, it may be another story. But for the trend part, it may be another story. For the trend part, the horizontal scale fluctuation, it seems to be much larger than the vertical ones. Okay, I guess I have run out of the time, so I will skip the mobilized value part.
Thank you.
So, okay, thank you.
Thank you.
On behalf of the International Society for Soil Mechanics and Geotechnical Engineering, congratulations on being awarded the 2023 Suzanne Lacasse Lecture.
Okay, thank you.
Our next speaker is Michael Grimm. Michael Grimm is Associate Director for Natural Hazards at the United States Geological Survey. He oversees a variety of hazards, including earthquakes and landslides. Previously, he served for over 25 years with the Federal Emergency Management Agency, managing risks and responding to disasters. Michael.
All right. Good morning, everybody. I am very pleased to be here with you. My name is Mike Grimm. I'm the Associate Director for Natural Hazards. Really want to thank you for having me here today. And what I want to do is to take us out about 30,000 feet higher and zoom in and talk about the many exciting things that we're doing at the USGS, particularly in the natural hazards mission area that I lead for the USGS. But first I want to introduce myself a little bit more since it's my first time with you all, and very excited to be here. So I just completed day 80 at the USGS, and before I came to the USGS, I served at the Federal Emergency Management Agency for 26 years, where I was fortunate to have a number of really fantastic jobs. Most recently, I led FEMA's Risk Management Directorate, and I was focused on providing quality hazard and risk data to the nation, promoting equitable investments in risk reduction, and strengthening partnerships that increase public awareness of risk caused by natural hazards, including climate change. So I spent many years at FEMA focused on equipping and compelling people in the nation to reduce disaster suffering for all. And I think it's the big green button, yeah. So across the nation, we're all seeing rapid development, new housing, new highways, new infrastructure, all across our landscape. And with the continued development across the nation and the compounding of impacts of climate change, we must be even more aware about how and where we build and how we manage our natural resources. So as we look to the future, we've really got to continue driving towards a more resilient and a risk-informed nation, but we can't realize that vision alone. It's really through partnerships where we can arm decision makers with science and risk information that they need to make sound and resilient decisions. And I see my new role at the USGS as continuing this important mission, creating a more resilient nation. So the USGS is a mission-oriented federal science agency within the Department of the Interior. We're also a far-flung agency with our 8,000 staff and a couple thousand more contractors, volunteers, and others located in 68 science centers in several hundred locations across the country. We work across a broad set of mission areas with a wide array of expertise, including geologic, biologic, hydrologic, and mapping sciences. You can see on this slide the 5 mission areas of the USGS. And what we do is we provide foundational data sets, we monitor natural phenomena, and we seek to translate our research on natural resources and hazards into information that's actionable by decision makers and the public. Bottom line is we want our science put to use. USGS has a responsibility to ensure that the research and data collection that we undertake and the resulting information that we deliver across our mission is useful to the public and for all. We want to ensure that our science can be applied to those who need it most. And our approach really relies on that thoughtful connection between user needs and research directions. So, for example, what challenges are people facing, and what is the scientific information needed to address those challenges? We're committed to engaging with partners before, during, and after the development of products to ensure applicability, and we use social science and data visualization and user testing to develop and improve our products. Our goal is to provide accessible and useful tools and products to guide decisions, both nationwide and at scales useful for local problems. One of the things we do in the mission area, in the natural hazards mission area that I lead, is to take that scientific research and development and develop hazard assessments and an understanding of the hazard processes that inform decisions and contribute to preparedness, response, mitigation, and recovery activities. So back to what I used to do at FEMA, I relied on the USGS data and research to translate information into action. And delivering these risk-based products really requires sustained investment in both monitoring and research capabilities and a commitment to valuing the communication of hazards and information in a clear, actionable, and equitable way. Many of the products that we work on are done in partnership with states and communities and academia, federal agencies in the private sector, and so many other different partners. So here's a snapshot of the natural hazards mission area that I lead that includes 6 programs: the earthquake program, the volcano program, landslide, coastal and marine, geomagnetism, and the global seismic network. So today I'm here to highlight our role in ensuring our critical structures and systems are resilient to the forces of nature and safeguarding lives, minimizing the impact of natural disasters. It's through our scientific research that we provide crucial data and insights into the behavior of natural hazards such as earthquakes and landslides, volcanic eruptions, and so on. And armed with this knowledge, engineers and designers, like you all, can help develop effective strategies to mitigate the risks. So our research informs the development of building codes and standards and guidelines that incorporate hazard-specific considerations. For example, incorporating seismic-resistant design or floodplain management techniques and slope stability measures, as we just heard about. Engineers can enhance the durability and safety of infrastructure. Ensures bridges and roads and buildings and other critical facilities can withstand the forces unleashed by natural disasters. So now I'd like to spend a few minutes to highlight a few of the areas in each of the programs where I think you might be interested and where there's potential for collaboration. So first, let me talk about our earthquake hazards program. We operate under the Earthquake Hazards Reduction Act of 1977, and that established the 4-agency National Earthquake Hazard Reduction Program, or NEHRP. That's a partnership between NIST and FEMA, the National Science Foundation, and the USGS. For the USGS, we coordinate our activities in 3 main areas. It's monitoring, hazard assessment, and applied research. So for example, the Advanced National Seismic System is a cooperative effort to collect and analyze seismic and geodetic data on earthquakes, to issue timely and reliable notifications, and to provide data for earthquake research and for hazard and risk assessments. Most recently, federal, state, and private investment has resulted in the West Coast earthquake early warning system called Shake Alert, which you may have all heard of, and it's built on the backbone of that advanced seismic network. Shake Alert began in California in 2019 and in Oregon and Washington in 2021. And we produce the alerts that are distributed through FEMA's wireless network, the emergency alert system for earthquakes magnitude 5 and larger. We're looking to the future how we can expand the program in other high-risk areas. Another area I want to highlight is our work to contribute to earthquake risk mitigation strategies. We contribute by developing seismic hazard maps and other products that describe the likelihood, potential effects of earthquakes nationwide, especially in urban areas of highest risk. And I'm very, very excited to share that we're nearing the end of an update process that will include all 50 states for the first time ever, and the final model that you see will be officially published at the end of the year. We're also working towards seismic hazard model updates for Puerto Rico and the U.S. Virgin Islands and Pacific territories, with that goal being set for delivery in 2026. So this graphic depicts the process of going from that earthquake science and research and the seismic hazard model that I just showed you to design guidance to international and statewide codes. So many of our different stakeholders, government agencies at all levels, architects and engineers, insurance companies, businesses, land use planners, emergency management officials, all rely on this USGS earthquake information to refine those building codes, develop land use strategies, safeguard lifelines and critical facilities, and develop emergency response plans. This past April, the U.S. Geological Survey and FEMA released a new report indicating earthquakes cost the nation an estimated $14.7 billion annually in building damage and associated losses. Compared to the previous estimates in 2001, 2008, and 2017, the annualized loss ratios have consistently decreased throughout the western U.S., indicating that the work that's being done to reduce building vulnerability has proven successful. But this is only reflecting the benefits in new construction for modern seismic codes, as well as the latest science and earthquake engineering research. It's the vulnerable older buildings that continue to bear much of the underlying risk seen in the loss estimates. But understanding how much earthquakes could cost the U.S. is critical to inform decisions about mitigation policies, priorities, strategies, and funding that could be used to mitigate these older buildings. So this is the slide about the biggest environmental disaster in 2002 that never happened. When the Trans-Alaska pipeline was built, geologists, including the ones working for the USGS, identified the Denali Fault as having evidence for significant strike slip movement. The engineers built pipelines, designed a system of Teflon slider bars and kinks to accommodate the motion, so that when the magnitude 7.9 earthquake struck in 2002, the pipeline slid to the end, but not past it, and not a drop of oil spilled, and that disaster did not happen. So all these activities that I'm highlighting in the earthquake space are essential for the USGS filling our role as part of NEHRP. So for example, the U.S. Seismic Hazard Map is the basis for the seismic provisions of the building codes that affect domestic construction costs estimated at $1 trillion per year. Next up is the volcano program. We deliver a mission with state and university partners working together to operate 5 volcano observatories in Alaska, Hawaii, the Pacific Northwest Cascades, California, and Yellowstone. Focus of the USGS volcano activities in the past few years has been the implementation of the National Volcano Early Warning System, or NVEWS, which provides a vision where each of the nation's more than 160 volcanoes are monitored commensurate with the threat they pose to people, property, and infrastructure, including air travel. Just this morning, I got alerts about one of the Aleutian volcanoes and air traffic control efforts, if any of you are signed up for those warnings. But you can see from this graphic, there's a compelling need to enhance public safety and minimize social and economic disruption from volcanic unrest and eruption. So we deliver forecasts, warnings, and information about volcano hazards based on the scientific understanding of volcanic processes to accomplish our mission. Our enabling legislation for the volcano program provides us with very, very clear direction for the program that we're implementing through our strategic science plan for 22 to 26. The goals of the plan are to implement the early warning system, work with land use and emergency managers to increase preparedness and risk from volcanoes, as well as standardize and update how we do volcano hazard assessments, including adapting innovative technologies for volcano monitoring, among many things. Here's an example of a long-term hazard assessment for Mount Rainier, where we identify locations at risk from volcanic hazards. And these types of products help guide local eruption preparedness plans. We're also making progress expanding and modernizing the lahar detection around Mount Rainier and working closely with Washington State Emergency Management and Pierce County. Landslide Hazards Program. It's actually the new Landslide Hazards Program. It was just authorized in 2021 by the Landslide Preparedness Act. We're working with a number of state surveys on a number of activities, including collecting data to improve post-wildfire debris flow hazard assessments and mapping landslides to support the development of a new landslide susceptibility map for the nation. Primary objective of the Landslide Hazard Program is to reduce long-term losses from landslide hazards by improving our understanding of the causes of ground failure and suggesting mitigation strategies. One of the areas that we've recently been focused on is the impact of wildfire that can have on landslide and debris flow susceptibility. Wildfire can have extreme effects on the hydrologic response of a watershed, and debris flow activity is among the most destructive consequences of these effects. As you all know, the recent fires in the western U.S. have impacted hundreds of thousands of acres of steep terrain, much of it's public land, making it susceptible to increased erosion and debris flow activity. This slide depicts some of the work we did in Colorado recently to the Grizzly Creek wildfire near Glenwood Springs, Colorado. I was just out there last month, actually, at the Association of State Geologists meeting, taking a look at some of these debris flows. What we did, the USGS assessments for these debris flows were used by the Colorado Department of Transportation, U.S. Forest Service, the National Weather Service to manage safety closures on that I-70 corridor through Glen Canyon in central Colorado during the summer monsoon season. The highway closure by the debris flows you can see, such as on the left picture there, results in a 100-mile detour around that section of I-70. I mean, there's just no way through. That's the only way through. So that obviously can have really significant impacts to communities along the corridor and really beyond the corridor. So taking that USGS science to action helps inform the decisions by federal, state, and local officials so that we can try to reduce those economic impacts. And overall, the type of work focuses on developing rapid and accurate methods to assess post-fire debris flow hazards and applied research needed to better understand the processes that control post-fire debris flow initiation and growth. The link between climate change and landslide hazards is evident in Alaska. Retreating glaciers, changes in precipitation patterns with increased rainfall intensity and higher snow lines, along with warming temperatures and the degradation of permafrost are driving landslide activity. This is another example of our work in Alaska, where a large, steep slope in the Berry Arm Fjord, 30 miles northeast of Whittier, Alaska, has the potential to fall into the water and generate a huge tsunami that could have devastating local impacts on the people who live and work and recreate there in and around Whittier and the northern Prince William Sound. Sticky pages. The USGS is working with federal and state partners to make use of the risk information. So finally, I want to touch on our Coastal and Marine Hazards Program that provides actionable science products, including characterizing the physical processes of the landscape in response to coastal change hazards, such as storms coupled with sea level rise, that addresses community needs around our nation's coasts. One of our focus areas over the coming year will be ongoing development of our coastal change models for forecasts of coastal response to different events and processes. This type of actionable science will help resource managers and communities understand the response to these coastal landscapes and help communities make risk-informed decisions. So this slide highlights both the risk and the overall economic significance of our coasts and why we need to be more resilient. You can see 40% of our population lives in a coastal county, and there's trillions of dollars in goods and services going on. And as sea level rises and storms increase, we only need to improve our predictability and resources to local managers. So let me talk about a portal. It's our Coastal Navigator. And what is our Coastal Navigator? It's a portal that you can enter. We've got over 54 different coastal and marine products in there. And you can go in there, put in your needs, see what products are in your geography or timelines and various other tools, and come out with different products. It really helps the user define what they want to do. So let me just talk about a couple of these to highlight. And this was designed with what we call human-centered design, which is problem-solving technique that includes the target audience in the development process of many of the tools, so that so they're actually useful to somebody. So first, out of the two products I want to pull out of the 50-plus products here, an event scale planning model. Well, did it change? There we go. So this is more of an operational model. Event scale, we coordinate a lot with NOAA on this product. It's used by emergency managers, for example, for evacuation planning. It looks at the tide, the storm surge, and the wave run-up. And you can see the example in the upper right corner there of the Outer Banks in North Carolina, operational model that helps understand when those road closures and breaches and flooding are going to occur, so for evacuation planning. Looking more toward the future, we're also doing future flood and erosion, and this looks at the combined effects of sea level rise and waves. And you can see the little model graphic that runs in there as we're modeling sea level rise and the impact across barrier islands, and really looking at that sea level rise and geomorphic response along our coast and how things change for longer term planning. All right, let's talk finally about marine geohazards, or dangers of the deep. That includes earthquakes, volcanic eruptions, submarine landslides and tsunamis, as well as the disassociation of gas hydrates, which can cause the seafloor to collapse, and oil spills and toxic seeps that impact sea life and the physical characteristics of the ocean environment. So at the USGS, we map the seafloor and what's beneath the seafloor to define the region's geologic framework. That information has broad applications in resource management and development. So for example, the nation's continental shelves are increasingly used for renewable energy. The wind lease areas occupy nearly 10,000 square kilometers of the Atlantic already, with more sites planned. And the nation's first large offshore wind farm is being built right now off of Martha's Vineyard in Massachusetts that you can see in the upper right corner there. In addition to the wind turbines, extensive transmission infrastructure, cables, basically, are being placed upon placed upon the seafloor and buried in the seafloor. So all of these types of structures require knowledge of the seafloor and the subsea floor to avoid and mitigate hazards, such as natural shallow gas and other zones, prone to intense scour and that sort of thing. So our understanding of our seafloor and how it changes are critical for that offshore development and long-term ocean planning. So in closing, I believe that empowering risk-informed decision-making for the nation must be at the core of what we do. And our ability to be risk-informed relies on the science conducted every day at the USGS by our amazing researchers. And our science and research plays a pivotal role in protecting our infrastructure through innovative engineering design, providing this valuable data, informing building codes and guiding engineering decisions. The Natural Hazard Mission Area ensures that our critical infrastructure can withstand challenges posed by natural hazards. Our collective efforts in education and outreach promote a culture of preparedness, ensuring that citizens are informed, proactive, and resilient in the face of diversity. And at the same time, risk can help improve the research that we do by helping us consider where we work and who we work with and how we conduct our research so it's responsive to the community's needs and the nation's needs. But as I said at the beginning of this, we can't do it alone. It's really through partnerships and working collaboratively and engaging in discussions, as we're here today, to lead that science to action. So with that, thank you very much. Thanks for having me. All right.
So next, one new attempt of this Geo-Risk conference is to invite 2 featured presentations for each plenary session. The first of such presentations will be given by Dr. Lin Yao Li. Lin Yao did his PhD study at the University of Maryland under Professor Greg Becker. He's presently a postdoc researcher at the University of Michigan. His study aims to enhance decision-making process in disaster response and urban planning. Lin Yao, please.
Hi, thank you so much for introducing me. So first of all, I want to thank for my advisor, Dr. Baker, Dr. Bensi, and my collaborator, Helen's contribution to this project. And my presentation topic is social media crowdsourcing for earthquake damage assessment. So you know, while some weather-related events like hurricanes and floods that may be forecasted, some sudden onset events just happened with little or no warnings. And these disasters, like earthquakes, present a particular challenge for disaster responders to estimate the damage because it's really hard to prepare the equipment and personnel for the damage assessment. So conventional earthquake damage assessment include like the remote sensing on-site investigation with the aid of the aircraft sensors or the cameras. However, these techniques often require some time to pre-deploy the personnel and equipment, and sometimes the process could be expensive. So another commonly used technique is the survey response. So one typical example is the USGS did you field map. However, you know, collecting the survey generally may take some time, like 1 day or 2 days, to inform the damage status. So are there any other potential data resources that we can leverage for the damage assessment? Especially, we want a cost-effective approach. So, you know, with the advancement of the internet, people nowadays are using social media to communicate. In particular, during the disaster events, people post a lot of messages and images online. So our study wants to leverage the information that posted by people, by the general public, and we want to study whether we can use the machine learning or some other natural language processing techniques to understand this information and to inform the damage status. So here are the motivation of our research. We chose the case study of 2019 Ridgecrest, California earthquake as a case study. This earthquake sequence consists of 2 major events. So one is the 6.4 magnitude foreshock, and the other one is the 7.1 magnitude main shock. And the epicenter is located at the Ridgecrest, California, and road cracks, building damages, and fires were reported in Kern and in New York counties. And also, significant damage was reported at the Naval Air Weapons Station China Lake, and people live in Santa Cruz, Las Vegas, and Los Angeles could feel the earthquake. So after the earthquake happened, we used the Twitter search API with the keyword earthquake to collect tweets for 1 week. And then we applied damage-related words like damage, injuries, cracks, to filter in damage-related tweets that can be used to inform the damage status. So firstly, I want to show some examples how we can connect tweets, how we can use tweets to inform the damage. Oh, I'm sorry. So firstly, I want to leverage some insights from Modify Macaulay because we need the damage level to know how we can classify the damage levels. So we leverage this MMI scale. So MMI scale has long been used in earthquake studies, and it consists of 10 shaking levels with level 1 implying no fault and level 10 implying extreme shaking. So however, this scale was judged to have too fine classification that might be hard for the machine to classify. So we manually create a simpler 4-step scale. So with level 0, So with level 0 for no damage, level 1 for slight damage, level 2 for moderate damage, and level 3 for significant damage. And then based on these insights, I want to show some Twitter examples. So in the first example, the person posted that start falling off shapes and walls. So this implies some slight damage. So it was classified as level 1. And the second example shows that there was no initial reports of damage or injuries from the assessment. So it was classified as level 0 because there was no damage happening. And the third example, the user posted that an earthquake shook Southern California open cracks in buildings, started fires, and damaged roads. So this has shown some structural damage to the infrastructure system. So it was classified as damage level 2. And the last example showed that the earthquake has collapsed some buildings. So it was classified as 3 because we feel the building collapse is a significant damage. So building on these insights, now we want to build the machine learning models to classify these tweet examples. So basically, this is a supervised text classification problem. And for text classification, the model consists of 2 parts. So the first part is to apply the word embedding techniques to convert each tweet into a vector of numbers or matrix numbers that could be understood by the machine learning models. And then for the second step, we apply several machine learning classifiers like the random forest, the naive Bayes, support vector machine, and logistic regression to classify the information into the 4 predefined classes, so level 0 to level 3. And then we train the machine learning models. We train multiple models based on the training data set. And then we test the performance on the testing data set. And then we apply several metrics to estimate the performance. So here's the result. So because this is our very initial attempt, so the results may not pretty perfect here. And in our current project, actually the performance, especially the F1 score, has improved a lot. So for our initial attempt, so the TF-IDA plus the random forest achieved the highest testing accuracy and the high F1 score for each class. So we apply the TF-IDA plus the random forest to our whole data set. And now I want to show the results. So before I show the damage assessment, I really want to show how the tweeted volume changes during the study period. So the image above shows the tweeted volume changes, with the y-axis showing the tweeted volume and x-axis shows the data and time during the study period. So we can observe there are 2 clear peaks during the study period. So that means when upon feeling the earthquake, people post a lot of messages online on Twitter. And correspondingly, we also calculate the average words per tweet and the average characters per tweet. So you can observe that in response to the 2 peaks of the image above, the average per tweet and the average characters per tweet decreased a lot, very sharply during the earthquake time. So that means when people feeling the earthquake, people just tend to post very short messages like, oh my God, there's an earthquake. Is that an earthquake? So generally, those messages are very short. And by applying the machine learning models, I want to show how we try to explore the damage pattern, the patterns of the damage assessment from both temporal and spatial perspectives. So for the temporal analysis, so we firstly bin the data in every 2 hours. So that means we calculate the tweets in every 2 hours since the start of the event. And the y-axis shows the Twitter-derived damage level. So it is based on Twitter data. And the x-axis shows the time. So we have 2 key observations here. So the first observation is that the final assessment converges to 1.4. So if you record our 4-step scale, so this is somewhere between the slight damage and moderate damage. So this is generally consistent with the news report and USGS report showing that most people during the earthquake just feel the earthquake with minor injuries and road cracks reported. And our second observation is that after the earthquake happened, so you can observe there is a clear increase of the damage assessment. So that is because at the beginning, people just reported that they were safe. But as the event, as the time went by, more cracks, more road cracks, more structural damages were reported on social media. So that So the damage assessment shows an increase. And the most interesting thing is that after like 14 or 16 hours, so the damage level just leveled off and shows a stable assessment. So this implied that if the disaster responders who wants to use social media to do a damage level assessment, they need to keep collecting the data for 14 or 16 hours. And then we also want to explore whether our social media, whether the crowdsourcing approach can show some spatial patterns. So we firstly applied the name entity recognition tool to identify locations from tweets. So I want to give you an example. So for example, if I posted tweets, say road cracks reported in Ridgecrest. So the name entity recognition can extract the location Ridgecrest from the tweet. So we, based on this extracted location information, we group the tweets based on the county information. And then we plotted the Twitter-derived county level damage as shown on the right side. And then we also want to demonstrate, we want to validate, okay, whether the crowdsourcing approach can show some consistency with the USGS intensity map. So we also created the county level intensity map based on the USGS. So we further plotted the correlation analysis. So you can see for this correlation analysis, the y-axis showed the county level. So this is based on the Twitter crowdsourcing approach. And the axis showed the county level MMI based on the USGS. So we can observe that there is a clear correlation between these two variables. And the R value is 0.85. So this high correlation shows that our crowdsourcing approach for this case has a good consistency with the USGS reports. So our research provides several implications. So the first implication is that our study provides several metrics that can help the disaster responders to monitor sudden onset events. This is because when the disaster happened, a lot of people posted messages online. So we suggest that the disaster responders can monitor these messages, like the volume, the words, and also like the average words per tweet, average characters per tweet. So use these patterns to monitor how people react to the disasters. And second, our study demonstrated that the value of crowdsourcing to process reports and damage. And third, we suggest that if disaster responders want to collect social media data to inform the damage, they need to keep collecting data for 14 or 16 hours to reach a reasonable assessment. And the last one, we want to highlight that our approach does not mean that our approach want to replace conventional approach, because the crowdsourcing approach also suffers some limitation, which I will cover. We want to highlight that this approach can be only used to complement the conventional techniques for rapid damage assessment. So I want to cover several limitations for the crowdsourcing approach. So the first one, the location identification. Because a user can mention several locations in the tweet, but our current approach can only classify each tweet as one damage level. And another thing, another limitation associated with the location is that I can post some tweets, say there was some damage reported between two cities, but we can't capture these fine-grained locations from the tweets. And the second limitation is the NLP text classification. Even with ChatGPT, with some large language models, there is still no guarantee that the natural language processing models can understand the textual information correctly. So the third limitation is the data set. Because we all know that people posted a lot of messages online, so this Twitter data, this crowdsourcing data contains a lot of noise. So if we want to use the social media data to inform the disasters, we need to guarantee how we can clean the data set for assessment. And the last limitation I want to highlight is that our approach is only suitable for minor and moderate scale earthquake. This is because when the earthquake is really heavy, people might lost the access to internet, so they couldn't post anything online. And also, our approach is only suitable for those areas, for the disasters happening in those areas where people use social media to communicate. So if people don't use social media to communicate, and then we couldn't use the crowdsourcing to inform the people's response and inform the status in the affected areas. So these are some limitations for our research. And last, I also want to capture this. I also want to catch this opportunity to introduce my research a little bit. Yeah, please give me this opportunity. So I'm particularly interested in using big data from Google Maps, from Twitter, and from Reddit with some applied AI, like the large language models, to study topics relative to urban planning, natural disasters, and health crises. Since the start of my postdoc, Since the start of my postdoc, I also expanded my research focusing on the online communities and also the application of large language models. So I know my research sounds a little bit different. So if you're interested in my research, I really hope to have more opportunity to talk with you after my presentation. And I also hope everyone will have a great time during the conference. And thank you all again for listening to my presentation.
Okay, so our next featured paper will be presented by Tong Chiu and Mike Belize. Tong is a professor of civil engineering at Penn State University. His research involves the application of physics-based machine learning in geotechnical engineering. Mike, on the other hand, is a research assistant at the University of Delaware. He recently defended his PhD thesis, so congratulations. Mike's research involves leveraging existing railroad inspection data to improve maintenance and monitoring practices, also using machine learning. So with that, please, the stage is yours.
Okay. Which one is the forward? Oh, okay. Which one is forward? Oh, okay. Okay. Thank you, Shadi, for the introduction. What I'm about to present is a collaborative effort between University of Delaware and Penn State University. My name is Tong Chiu. I represent the Penn State team. I would like to direct you to the figures on two figures on this slide. As we all know that railroads are important linear infrastructure. As railroads pass through mountainous terrains, we need to use the cut slopes. And these slopes are subject to instability risk. And land slopes failure events may deposit debris onto the track, which may delay the train operation. In some instances, it may cause derailment if the train operator is not notified ahead of time. Since it is very important for us to properly assess the risk of cut slopes along railroad tracks. So today, I will just discuss how to properly assess this risk by using geospatial information and track maintenance video. So first, I will discuss an overview of our research approach by using just one slide. And then I will discuss a case study area. And then I will discuss geospatial data analysis, which involves machine learning and landslide susceptibility mapping. And then I will turn it over to my co-presenter, Mike. He will discuss track maintenance video analysis, and then he will talk about how to combine the risk to do the overall risk assessment, and then at the end, we'll make a conclusion. So let's take a look at the approach. The essence of our approach is to combine the two risk assessments at different scales. So we look at the core scale, then we want to look at the landslide susceptibility of the overall area. So we do this landslide susceptibility mapping using machine learning. So when we use machine learning, we need to have input data. So one of the input data is the landslide inventory of the site and its vicinity. Another input data would be the landslide contributing factors or features for the machine learning model. So the output will be a probability of failure, which ranges from 0 to 1. And at the final scale, we can look at the railroad maintenance videos. We know some features, they are precursors to instability. For example, if you have a leaning tree or if you have a hummocky grounds. So these features are precursors to instability. So we look at the railroad maintenance video, we do object detection, and then we count how frequent these features occur in this video. That would give us the indication on the risk at the final scale. So eventually, we combine the two risks at different scales that will give us an overall risk of these instabilities. So let's take a look at our study area. It is a portion of the Amtrak's Harrisburg line. So for the international audience, I would like to say that Harrisburg is the capital city of Pennsylvania, and Amtrak is the national passenger train operator of this country. So this portion is about 9 miles long, and the Amtrak has identified the 11 geohazard sections through its maintenance program. Essentially, they look at their maintenance program, they found that they have to frequently send the crews to clean up the landslide debris in these 9 geohazard sections. So this on the lower right, we show these 9 sections highlighted using rectangular boxes along this line mile section. So for our machine learning model, we need to have input data, which is part of it is our landslide inventory of this site and its vicinity. We use the USGS landslide database, and we have identified 166 landslides in this area, and the location of these, they are shown in this figure. And then we also need to have input features for landslide susceptibility mapping. So these are essentially landslide contributing factors. So we have used the 10 contributing factors. These are elevation, slope, aspect, and multi-scale topographic position index. This can be obtained from USGS's 3-dimensional elevation program, which has a spatial resolution of about 10 meters. So essentially in this program, we know the elevation of every single point of the continental USA. And if you know the point elevation, you do a derivative, you get a slope. And then you can also get the orientation of the slope, because we find that the orientation of a slope is important for some landslide. And then we also have a normalized difference vegetation index, NDVI. We get this from Landsat 8 satellite imagery, which has a spatial resolution of about 30 meters, because essentially NDVI tells us the vegetation cover. If you have a higher vegetation cover, then you are less likely to have a landslide. And we also have a sand content, clay content, bulk density, and the field capacity. So these are the soil parameters we get from soil grids or open land map. These are embedded in Google Earth Engine. It has a spatial resolution of about 250 meters. And at the end, we have this annual average precipitation. You get this from NASA's DayMat. It has a spatial resolution about 1,000 meters. So we feed all this into a machine learning model. We do a supervised learning. So eventually, we will get a landslide susceptibility map of this study area. So on this figure, the green simply meaning that low risk, and the red indicates very high risk. So, and then we can see that the railroad identified 11 geohazard sections generally coincide with high-risk areas highlighted in red. So essentially, this one says that our risk assessment at the core scale works. So I'm going to turn it over to Mike. He's going to discuss how to assess this at the final scale.
Thank you, Tong, for the great discussion of the geospatial data analyses. So I'm going to talk about how cut slope hazards were assessed locally using right-of-way inspection videos recorded by Amtrak's inspection program. So on the slide, you can see 4 images extracted from the right-of-way inspection videos showing 4 different geohazard sections along the Harrisburg line. Even though the images are relatively low resolution at 480 pixels, there are still interesting slope characteristics that can be identified in these images. In the middle and bottom rows of the slide, you can see annotated labels in the images showing features of interest that were manually identified and detected features identified by the object detection model I'm about to describe. So an object detection model was trained using transfer learning. There was 1,280 annotated images of 4 feature classes: leaning trees, hummocks, rock faces, and moisture instances. The features were satisfactorily detectable, with leaning trees being moderately detectable, as seen in the precision recall curve. So to actually assess risk using this model, all inspection images not used in training were assessed for objects, which this table summarizes. This table shows a few really important features of the model. First, instances were most often detected in geohazard sections versus non-geohazard sections, as expected, as well as showing that there were many feature instances identified across the study area. For the 9 inspection videos, we did find some detection discrepancies, most often explained by differences in seasonal foliage coverage. That's most, the evidence of that is mostly seen in the leaning tree detections, where for some inspection dates we had numerous leaning trees, and for some we had 0. So this led us to perform the risk assessment statically. This table here shows, after combining all of those detection results together, we wanted to look at those detection results by geohazard section, which this table shows. By spatially referencing the images, we were able to do this, and we immediately saw that there were differences in the detection results by geohazard section. For example, if you look at geohazard section number 8, you can see that very few leaning trees and hummocks were identified, while many rock faces were identified. This geohazard section turned out to be a rock cut. Conversely, if you look at geohazard section number 11, you see many leaning trees and hummocks, but fewer rock faces, and this turned out to be primarily a soil slope. So the main result of this research activity can be seen on this slide. There are 3 plots showing the risk scores plotted continuously along the extent of the Harrisburg line, compared against the geohazard sections identified by Amtrak. The top plot shows the detected object densities, or the density of feature instances identified across those 9 inspection videos, and we see pretty good agreement with the geohazard sections. This score was normalized to fall between 0 and 1. Similarly, the landslide susceptibility map that Tong described was sampled along the Harrisburg line at the same sample rate of 1/100th miles. And again, we see pretty good agreement with the geohazard sections. The combined risk score was a point-wise multiplication of both individual models, and we found that the combined score had better agreement with the geohazard sections than each individual model. So without geotechnical measurements, we weren't able to quantitatively validate these results besides the satisfactory agreement with the geohazard sections. So what we did is we looked at some of the right-of-way images extracted from the inspection vehicles to see how well they agreed with the model results. What we found that we found that the highest risk scores were calculated at slopes that were relatively steep within the study area and relatively tall within the study area, with little to no vegetation coverage and made up of both soil and rock. That is what is shown in the top left and middle figure on this slide. Interestingly, the highest hazard score calculated outside of a geohazard section was at milepost 90.5, which was a fill section. So interestingly, this has a steep slope, but that slope does not go towards the right-of-way, it goes away from the right-of-way. So we found that interesting as well. So the primary conclusion of this research activity was that cut slope failure risk can be effectively assessed using machine learning methods of remotely sensed data. At the broad scale, we used landslide susceptibility mapping using landslide contributing factors and landslide inventory, and at the finer scale, we used object detection of right-of-way features. After combining these 2 models, what we obtained was a mechanism to look at cut slope hazards using only remotely sensed data that can help railroad engineers and geotechnical engineers prioritize certain geohazards of primary interest for potential remediation, measurement, or geotechnical investigation. With that, I would like to thank Cientis's UTC program for funding this research activity, Amtrak for providing the terrain inspection data, and USGS for the landslide inventory. Thank you.
All right, so I would like to thank the speakers for respecting the time, and that left us with room for questions. So I would like to open the floor for questions for any of our speakers for the remainder of the session. Questions? Yes, so we'll get you a mic.
The speaker, the USGS, he referenced a site for the tools that you could go onto and plug in data, but I didn't see where that was referenced.
Yeah, I'll be glad to provide the link and get that to you.
I have a microphone.
Yes, thank you. Yeah, I'll be glad to provide the link. And can you email it out or something? Or there's a website. I'll be glad to get it to you.
Sure, I mean, we can share it once you give it to us. Thank you. Any other question? Yes, Sisi. So please, we need a microphone. Thank you, Christina.
Yeah, the question is for Dr. Ching about uncertainties. In your very interesting presentation, I was wondering how can we advance codes and practices using the different types of parameters that you showed that quantify uncertainties in space and in point, especially in the United States. And I noticed that also from the tables you showed in your presentations. The CPTs are not the main means of doing subsurface investigation. So I'm wondering, when you have SPT instead of CPT, where your sampling is not is not continuous, how much this translates to your uncertainty? That was one question I had. Actually, I had a lot of questions. They're very interesting because our practice here is really we do an average and a plus minus standard deviation within sites, right? And what you are showing us is very important to understand how well you understand a site. The question is, how could we incorporate uncertainty quantification in codes and standards? And also, what I understood is that your conclusion about what is the most proper characterization of uncertainty has to do with the problem you are looking at. So whether it's a slope stability or it's a settlement, I'm wondering if you put one more dimension to it and it's a dynamic problem, then there are other parameters in there. So I know it's a lot of points. I'm reading through my notes, but yes, my main point is how do you see this evolving into the practice of geotechnical engineering? Thank you.
Very difficult to answer the question. First of all, I think you're asking about the codes. How do we implement the result of the research to the codes, especially when we do not have sufficient site-specific information, such as CPT, and we only have SPT. Also, if the let me try to answer your question in this way. If we do not have sufficient site-specific data, then we probably need to rely on past experiences, such as as you can see in my presentation, we have some tables showing the ranges of some, say I mentioned the vertical scale fluctuation varies in a narrow range, or the vertical smoothness also vary in a narrow range. So if indeed this is true for many sites, if you go to a future site, even you don't have any site-specific data, you can base on this prior knowledge that those parameters are narrow, within a narrow range. You can adopt that narrow range as your prior information for your design for this particular site. Okay, but now the challenge is that some parameters are indeed in narrow range, such as the vertical scale fluctuation and the vertical smoothness, but some parameters seems to not in a narrow range. As I shown in the presentation, that the trend part, the scale fluctuation for the trend, they don't seem to within a narrow range. For that part, I will say it is hard to get those parameters without some amount of site investigation. Yeah. Another possibility to address your question is that even though for those for some parameter we don't have a narrow range, but there's so-called in the previous research, some people talking about the worst case scale of fluctuation. Some people do random finite element simulation. They found that there are some particular scale fluctuation that you have. When you have that scale fluctuation, the thing will become the worst. Say, for instance, your failure probability becomes the largest. Another way to address your question, if you don't have that sufficient site-specific data, we may need to come to the worst case scale fluctuation for design. Yeah.
Thank you, Jianye. We have a question in the back.
She was first, actually.
Oh. Okay.
Thank you very
Ladies
much.
first. Yeah, go ahead.
I had a question for the social media crowdsourcing. Yeah, thank you very much for this dynamic presentation. I was wondering if you're actually considering working on images and videos, since social media approaches, the ones who post most are young generations, and I think other social media platforms can be very resourceful. So are you considering videos or images?
Hi, thank you for your question. I think this is a very, very good question because we all know that different social media resources have different types of images, different types of messages. Like I know a lot of young people using like TikToks to communicate, right? And many others use like Instagram. So I think different social media platforms have different advantages and disadvantages. So I want to give an example. So I think, for example, if we want to use Instagram, because we all know that a lot of people use Instagram are young people, so they like to show their images. So they like to show their lives. So we feel that like for this kind of study, we feel maybe Twitter provides the best data resource. Yeah, and we also feel that maybe like TikTok could provide some good results because TikTok right now is very popular and they can show the videos. I think some videos can tell more information. Yeah, and I think another very interesting thing is, actually I'm thinking about this is because we all know that Twitter allows us to post messages and images at the same time, right? So I think a very, very interesting idea is whether their image and text information can show some consistency. Yeah, because we feel that sometimes, for example, I think in my example I show, one user also posts some images like the house fires, and then in the text, the user also mentioned house fires during the earthquake. So in this case, that these two information resources show some consistency, but it is possible that in other cases, the image and text shows some different information. So I think in the future, I will consider the image and video information, especially for the hurricane damage, for the hurricane damage estimation. I think this is a very, very good suggestion. Thank you.
Thank you. So we still have time for one question, or maybe another. Okay, so two.
My question is for Professor Jianye Ching.
Yes.
Thank you for your talk. It was very interesting and illuminating. I was wondering how specific to a particular sedimentary environment are those results that you have presented? I mean, the Adelaide case, what kind of deposit was that? Or do you expect that to generalize?
For that site, it is a stiff clay site. Yeah, and according to Professor Mark Jaksa, he described the site as a relatively uniform site. And even though it is a relatively uniform site, you see all the quite significant horizontal variation. And I can share with you, Marcos, by myself, I have analyzed quite some sites. And that kind of horizontal variation is not uncommon. In my experiences, maybe 50% of the cases have that kind of horizontal variation.
Thank you. Thank you, Jianye. So our last question, a quick one, and then we'll ask Brad to come over.
To Professor Ching. Jianye, thank you very much for this beautiful lecture. Your methods are quite sophisticated. I'm familiar with your theory concerning this movements, and I agree with you, but what you showed today, it seems to be controversial, because the statement that the horizontal fluctuation scale could be shorter than the vertical seems it's against my intuition. If we rely that we are able to describe the spatial variability by stationary random field, it means that somewhere there is an assumption that we are considering geological deposits which are usually horizontally situated. And it comes also from the stress analysis that it should be that the correlation in the horizontal direction is larger, because this is intuition, okay? The other thing is that if we assume that both horizontal and vertical fluctuations are very short, that it means it looks like a chaotic, it looks like a Brownian motion, which is, I think, not observable. I'm sorry, that's maybe I'm not so deep in what you showed today. I know your smoothness theory. Okay, but
okay,
thank you.
Thank you, Vulture. The analysis, I know what I am presenting today is controversial, and I also thought the horizontal variability should be milder than vertical one. What I showed today is this. One part seems to be controversial, but the other part is not. What I showed today is that I think Professor Van Mark, he had a right observation in his 1978 paper. He said there seems to be two superimposed scale fluctuation in the soil data. That is consistent to our observation too. One scale fluctuation is for the spatial variability part. The other scale fluctuation is for the trend part. That is also our observation. Okay, this is not only true for the vertical direction, it is also true for the horizontal direction. And what I'm showing here today is a real case history done by Professor Van Mark. For that case history, it is true that the horizontal scale fluctuation for the spatial variability part is actually a little bit smaller for the vertical scale fluctuation for the spatial variability part.
Thank you, Jianye.
Okay,
and we can continue this later.
But
it's not gonna finish here.
Another table shows that for the trend part, it is consistent to our intuition. For the trend part, the horizontal scale fluctuation for the trend, for the horizontal trend, is larger than the scale fluctuation for the vertical trend. Okay, I'll discuss with you for the detail. Okay.
It needs a coffee or a dinner. I'm not sure. I mean, either this or that. So, Brad, the floor is yours to close the session. Thank you very much.
I don't ever go anywhere without some props. So we're going to talk about those in just a minute. But the first thing I want to do is say thanks to everybody for coming to Geo-Risk. This is the first time since I've been at ASCE, which is like 7.5 years, that we've had a conference in this area, which we live here. ASCE is about 20 miles northwest. We call this area the DMV, District, Maryland, and Virginia. So this is the first conference we've had in the DMV since I've been around at ASCE. And so we're really happy to have a home game. It makes things a lot easier. And we're really happy to welcome everybody to the area too. Please get out and see stuff while you're here. A lot of tourists never make it to Virginia when they come down here, or up here, I guess. You can go to the September 11th Memorial over at the Pentagon. You can go to the Air Force Memorial. It's those big pointy things that you see in the sky over there. Arlington Cemetery is right here. Mount Vernon is close. There are a lot of really cool things, so please go see those. The second thing I want to do is say thanks to our committee who planned this. Geo-Congress is a big deal, and it's a lot of work, and I have to do a lot of the work. Specialty conferences, the committee pretty much does everything, and we just show up and support them and help them along. So for Shadi and Limin and Bob and really, Jianye, everybody on the committee, thank you for all the work you did to make this happen. And it's really cool that we're all finally here together actually doing this. So we really appreciate everything that you put into this. The last thing I'll do before the announcements is tell you, when you go down to the exhibit hall, we all want to support Geo-Institute student programs, right? We give you some great ways that you can do that. I hold in my hand a Carl Terzaghi bobblehead. If you've ever thought to yourself, man, I would love to have a Carl Terzaghi bobblehead on my bookshelf. Even if you have never thought that before right now, you can make it happen. We have them downstairs. We have a giving program called the 96 Club in GI because we were founded in 1996. The idea is you donate $96 to student programs every year and you get something really cool. So the first thing we did were these Carl Terzaghi bobbleheads. We have a few left. The next thing that we did are these beautiful GI socks. Look at that, Strata. These are also $96. We have them downstairs. And then we have a couple of other things, too. The winning design from the student competition for T-shirts, the Geo shirt competition, we have some of these left downstairs. These are $25. And our social media campaign this year is Feel the Teal. Look at that beauty. Those are also $25 downstairs, and all the money goes to student programs. So if you want to support our students in the competitions at Geo-Congress, the grants that we give throughout the year for them to do various small projects, it's a great way to do it. Now the announcements, and then we're going to go to the break. If you did not get a card with the conference proceedings information, you can stop by the registration desk and pick one of those up. Make sure you read the proceedings. We put a lot of time and effort into those, so you should read all the papers. PDH forms are also available out there, and if you, if you're a conference attendee, which you are because you're here, you'll get an email in about 4 weeks with instructions on how to generate your certificate. In a minute, we're going to go down to the exhibit hall and see all the exhibitors who very generously put their time and effort and money into this conference. Please go talk to them because they did that. And a thank you also to our sponsors for the conference. We have an ASCE and GI booth down there, information on GI programs, publications, all kinds of free stuff. And you can donate to student programs there as well. We do have a special event tomorrow night, the Monuments by Moonlight Tour. It's a great way to get out and see some of the monuments in DC after dark, which is especially cool. We're meeting at 7:15. It leaves at 7:30. Spots are limited. If you'd like to go, there's a sign-up sheet at the registration desk. We would love to have you there. And we will be back in this very room for more keynote and plenary presentations at 4 o'clock today, so please find your way back here this afternoon. That is all I have. Thanks for sticking around this morning. Thanks, Jianye, for a great lecture. And everybody have a great day.